In section 5.4, we had just seen how if you compute an area function for a certain function, that gives the area under the curve f of t from t equals a to x, so that's setting up an integral here. If you find that area function, like we did with this example, and then take its derivative, you end up just getting your original function back, like little f, but with x inside of it instead of t. Okay, which was kind of a funny thing to see happen there, but it was not a coincidence. This is actually part of the Fundamental Theorem of Calculus, Part 1, or FTC 1 for short. And this says, if little f of x is continuous on the interval from a to b, then big F of x, which is the area function there, the integral from x or a to x of f of t dt, that is continuous on the interval as well and differentiable on the open interval. And big F prime of x equals little f of x. Okay, so there's a lot going on in this definition here, but that is the main thing that you need to focus on there. Okay, so if we're taking big F of x as an integral from a to x, f of t dt, okay, so if capital F is defined by an integral and you take its derivative, d dx of that integral from a to x, f of t dt, you are just going to get little f of x back out of that. Okay. So what this is essentially saying is that a derivative operation will kind of do the opposite thing as this integration. So you've integrated the function little f of t, and then when you take its derivative, d dx, you just get little f of x back. So it's almost like you've done essentially nothing. It's like you're stripping away all this extra stuff and you just get your integrand back, except now it has an x inside. Interesting. Okay, so usually a question that comes up at this stage, by the way, is, okay, why is it an x inside of there now? Why is it not a t? And that will become a little bit more apparent when we look at FTC Part 2. But as a quick answer for right now, remember when we would actually take the area function from a to x, you end up getting a formula. The area function is a function of x itself. So when you take the derivative of that with respect to x, there are no more t's involved at this stage. Okay, that process of actually finding the area strips away the variable t. All right. But for right now, we're going to focus on this idea of basically the derivative and the integral undoing one another with some examples here. We're going to find big F prime of x for the following. Starting with big F of x equals the integral from 3 to x of sine 4t squared plus 5 dt. Okay, so when we look at this function, we can see that this is set up in the direct format we need for FTC Part 1. We have an integral, we have a constant on the bottom, that's the a value, it's 3. We've got plain old x on top, that's good. We need that. So this inside of here must correspond to f of t. All right, and it does. This is f of t equals the sine of 4t squared plus 5. Okay, so if we set this up to find f prime of x, that's taking the derivative with respect to x of the integral from 3 to x of sine 4t squared plus 5 dt. Or if you like, for right now, you could put a little f of t in there, right there. All right, f of t dt. We know that f of t is that sine function. So this literally looks exactly like what we're seeing in our definition box up here. All right, derivative with respect to x. We've put a 3 in for the constant a, but then there's literally f of t dt inside of the integral. So we are going to get little f of x by FTC part 1. And so what that's going to be is plug an x into your f of t function. You'd get sine of 4x squared plus 5. And that right there is the derivative. We didn't even have to actually compute this integral. There was no Riemann sum involved here. We just took our f of t and we put x into it because that is what FTC part 1 essentially allows us to do. The derivative undid the integral. All right. Now, it's not always quite that straightforward. If we look at our next example here, we have big F of x equals the integral from x to 5 of 3 square root of t plus 1/5 t to the 8th dt. Okay, so look at this for a sec. Look at our definition box and the previous example and see what's wrong with this picture. What is preventing this from being set up exactly like our area function in the definition box there? Okay. If you said, hey, the x is in the wrong spot, you were correct. This integral has its limits switched from what we're seeing in our theorem up here. X should be the upper limit of integration for this theorem to work like it does. And here in this example, x is the lower limit of integration. So that right there, that's our problem. The limits are switched. Okay, but if you'll recall back to section, I believe 5.3, properties of the definite integral, we got something for this. So recall, if you want to switch your limits of integration, like let's say they were going from b to a, all right, of some function, if you wanted to switch those around and go from A to B, do you remember what we need to do? Throw a minus sign out front. All right, if you switch your limits of integration, you get the negative of your integral. And so that's what we need to do here. So let's rewrite our function, big F of x, as being negative integral from 5 to x of 3 root t plus 1/5 t to the 8th dt. And now we have what we want here. Okay, we've got our constant on the bottom, the lower limit of integration, a equals 5. We have our x, plain old x, in the upper limit. Now that's good. And so what's inside of here must be f of t dt. So here's f of t. It is 3 square root t plus 1/5 t to the 8th. Okay, so if we would like to take the derivative of this function, f prime of x, take d dx of that whole business right there, negative integral, stick our function in there. I'm just going to write f of t for short right now. F of t dt, there we go. Okay, notice how that negative that we had to incorporate, that is literally just a constant multiple, multiplying the thing that we're trying to derive. Okay, so we can pull that -1 out to the front, negative d dx of our integral 5 to x f of t dt. And so this expression right here fits with what is expressed in our theorem. Okay, so that matches up with this part of our theorem. And so that is going to give us f of x right there. Now we do still have a negative to contend with here, but that is okay. We're just gonna string that negative along, negative f of x. And so we're gonna have for our result negative, and put in your function little f of x, 3 square root x plus 1/5 x to the 8th power. And there is our result. Okay. Now one more example here. We've got f of x equals the integral from 0 to x cubed of sine t dt. And okay, pause for a second again, take a look at that integral, take a look at our theorem up here. What's the difference between this setup and what we would like to see? All right, did you spot it? It is the x cubed in the upper limit of integration. We want that to be just plain old x. We've got our constant in the lower limit. 0 is fine. F of t looks okay. It's sine t in there. So yeah, the x cubed is going to be the issue with this one. All right. So yes, the fact that this is not just a plain old x is going to be kind of a problem. It is a little function of its own. X cubed is a tiny little function. And so we have a function of x within our thing that we are trying to take the derivative of. So a function within a function, we are going to need to use the chain rule to take this derivative. Need to use chain rule. Okay, so how we're going to do this, well, one way to approach it would be to say that, let's see, how would be the best way to look at this? I'll show you guys one way, and then if you can think of a simpler way, there are some other ways to think about it. Okay, so one way to approach this is to put some other variable in the place of x cubed there. I think we did this at first when we were looking at the chain rule. We let something like u equal the function that was complicating things for us. All right, let u equal x cubed. So then we could rewrite this function as like f of u instead of x. That would be the integral from 0 to u of sine t dt, because changing from x to u didn't really change anything about t. That part's still fine. Then our chain here would look like this. If you're trying to find f prime of x, you would take f prime of u and then multiply by the derivative of u, the inner function, u prime of x. Or if you'll recall, in Leibniz notation, df dx would be df du times du dx. Okay. And this is where we're working with big F of u equals this expression right here with the integral. And its derivative, now, big F prime of u would equal little f of u, because this function is set up now in terms of our theorem. All right, it does say u instead of x. Okay, I'll give us that, you know. There's a u right here, but there's also a plain old u for our upper limit. So it is set up in the way that we want. So when we're trying to take du of this integral, which is in terms of u now for its upper limit, we would get little f of u instead. All right. And if we've seen here, this is our little f function, little f of t equals sine t. So little f of u would equal sine u. And then our derivative of u with respect to x would be 3x squared. That's from this right here. U equals x cubed, so the derivative of u with respect to x is 3x squared, little power rule. All right. So we would say from all of this that big F prime of x would equal, all right, big F prime of u, that's sine u right here, sine u times u prime of x, which is right here, that's the 3x squared, like so. But you know, we don't really want to mix our variables here. We do want this all to be in terms of x now. That's the specified variable. So this u right here is not going to be any good, really. We need to switch that back to terms of x. So we need to throw x cubed back in there. So sine of x cubed times 3x squared. Okay. So big F prime of x for the final answer on this one is going to be 3x squared times the sine of x cubed. And there we go. All right. Now, just for a real quick alternative approach on this one, I know that we have used the covered up approach for the chain rule a lot. So this via cover up. F prime of x, we would cover up our upper portion there. And so we would take the derivative of this integral from 0 to pink blob of sine t dt. And that would give us from our theorem, it's like this type of thing, but with pink blobs. Okay. So you're going to end up with f of the pink blob. All right. So we go down there and we put little f of the pink blob times the derivative of the pink blob, d dx of pink blob. Highly scientific. Okay, and so then you would uncover your pink blob and see that it is actually x cubed. And so you would say, okay, this is little f of x cubed times the derivative with respect to x of x cubed. And that's when you would use your f of t equals sine t. So f of x cubed is going to be sine x cubed. And then the derivative of x cubed is 3x squared. And so we would ultimately end up in the same place there, 3x squared sine of x cubed. Okay, so either way that you choose to approach this, you'll end up with the same answer. But the overall gist of this one is that if it's not just a plain old x in your upper limit, you need to use the chain rule in some way or another. All right, if the limits are switched, make sure you throw a negative, or if it's set up exactly like the theorem calls for, then you're just good to go with little f of x.